So we're going to have a look at the properties of ionic compounds. You should be aware of ionic substances as being a metal reacting with a non-metal. Metal's usually left-hand side of the periodic table, non-metal's usually the right-hand side of the periodic table. And you should be aware of how to draw out the way the electrons transfer to show the origins of the ionic bond. What we're going to look at now is the physical properties of ionic compounds. If you do certain things, what happens? And the things that we're going to look at are melting point and boiling point, and electrical conductivity. Electrical conductivity when the ionic substance is solid, electrical conductivity when the ionic substance is a liquid, when it's molten, and the electrical conductivity when it's in solution, when it's dissolved in water. Before we do that, we need to look at the way that the particles are arranged in an ionic compound. And here's quite a nice simple diagram that I've stolen from BBC Bite Size. What we've got here is your chlorine ions, chloride ions here, and they're negatively charged. And if it was sodium chloride, these would be the sodium ions. Don't worry about the size difference, I'm not particularly focused on that. The crucial thing is that we've got sodium positive, chloride negative, sodium positive, chloride negative. It alternates, and you'll find that a sodium is never directly next to another sodium, it's only next to chlorides, and chlorides are only next to sodiums. So this is a flat arrangement, how it looks, and if I add this picture here, just bear with me, oops, undo, add this one here, that tells you a little bit more about the three-dimensional arrangement of that. So what we've got here is a flat layer of the sodium chlorides alternating, but here you can see there's a block here, and then behind it another layer, and another layer, and another layer. So we've got what's called a three-dimensional arrangement of alternating positive and negative ions. The key phrase that you need to be aware of is giant ionic lattice. The giant part of this implies, it doesn't actually happen, but it implies it's really, really big, and it almost goes on forever, because next to this sodium it's a chloride, next to this sodium chloride it's another sodium, and it goes on and on. That's the giant bit. The ionic bit is easy because it's made up of ions, and remember, an ion is a charged particle, any charged particle. We've got negative charged particles, the chlorides, and positive charged particles, the sodiums. The lattice is that regular arrangement of ups and downs and crosses, and that's where we get the phrase giant ionic lattice. Okay, so I want to focus on melting points and boiling points first of all. If something melts, these bonds holding these ions together have to break apart. At the moment, what's happening is these particles are being held together in the giant ionic lattice, and that's why it's a solid, because they're held together. Remember, these things here are tiny, so one on their own we're not going to be able to see. Once you've got zillions of them bonded together, that's when you see your salt crystal, your sodium chloride crystal. If we wanted to turn this into a liquid, we would then have to enable each of these particles to be able to move around. The only way in which we can do that is by breaking these bonds, and to do that we just need to heat it. How many bonds have we got here? You can see there's loads of bonds here, and they're strong bonds. So in terms of melting points and boiling points, would we expect your ionic substance, bearing in mind there's lots of strong bonds, would we expect the melting point and boiling point to be low or high? And I've just looked it up. Sodium chloride has a melting point of 801 degrees Celsius, a very high melting point, and its boiling point is way higher than that, 1413 degrees Celsius. So ionic substances generally have high melting and boiling points. Okay, so just to repeat, ionic substances usually have very high melting points and boiling points because there are lots of strong ionic bonds. Lots of and strong ionic bonds. Okay, I hope that makes sense. We're now going to have a look at the electrical conductivity. So I'm going to come back to my simple diagram here. Now, if a substance is going to conduct electricity, there must be charged particles that are free to move. Now, hopefully you'll be able to see in my diagram here, when sodium chloride is solid, these positive charges are being held in place by the negative charges, and the negative charges are being held in place by the positive charges. So when sodium chloride is solid, we do have charged particles. Are they free to move? All they're doing is vibrating in position. They're not actually moving position. So solid sodium chloride does not conduct electricity. Solid sodium chloride does not conduct electricity because the charged particles, they exist, they're there, but they're just not free to move. If we were to heat the solid sodium chloride until it became a liquid, we're not adding water to it, we're just heating it. What we're doing is we are heating it until these bonds actually break, and then the ions, the charged particles, are then mobile. They can move around, the bonds have broken. So in that case, with liquid sodium chloride does now conduct electricity. So we've heated it, we've broken the bonds that are holding those ions together, and those charged particles, the ions, are now free to move. And lastly, aqueous sodium chloride does conduct electricity. And the reason it conducts electricity is because, again, the charged particles are free to move. Why are they free to move? We haven't heated it to break those bonds, but what we have done is we've added water, and the water is able to break those bonds. The water has broken the bonds holding those ions together. So, to recap, the melting point of ionic compounds is high because there's lots of strong bonds. The electrical conductivity when it's a solid doesn't conduct because the ions aren't free to move. When it's a liquid, we heat it until the bonds do break so the ions are free to move, so it does conduct electricity. And when it's aqueous, when it's in solution, the water is able to break those bonds, and therefore the ions are free to move, so it conducts electricity.